What we see then is that at first nothing tried to flow through, and then after a while things flowed through, but then when it started to slow down, the inductance coil kept pushing it through, so now we get a positive charge on this side and a negative charge on this side. Now it starts to rebound and go backwards. Now the positives start to flow this way, again really an absence of negatives, negatives flowing that way, and at first it resists. But then after it resists, then after it starts to die down, it starts to pump out more, and it brings you back to this. And what we see is that this circuit essentially oscillates. This is an oscillation that happens in the circuit. So we should be able to show what the frequency is here that this actually oscillates with. And again, this is an oscillating circuit that can be very, very useful for many reasons when you're taking a look at designing a circuit or anything. Even if you think about the possibility of sending signals or anything like that, creating an electromagnetic field around here. But here we go. So this thing is going to oscillate, goes back and forth and back and forth and back and forth. But let's look at the energy involved and see what we can get there. The total energy will be the energy in the inductance coil plus the energy in the capacitor. Well, the total energy, the energy in the inductance coil is 1/2 Li squared at any time, and the energy in the capacitor is 1/2 Q squared over C, no squared there. And this is the energy. There might be some energy in the inductance coil, there might be some energy in the capacitor. And so let's see if we can show that oscillating behavior. So I'm going to take the derivative of this whole thing with respect to time, dut dt. This du dt is the derivative of energy with respect to time. Well, energy doesn't change with respect to time. The energy in this circuit must be constant, so this must be 0. Now I take the derivative of this. I get, the derivative should be Li, and I gotta do the chain rule, di dt, plus this becomes Q over C dq dt. Well, remember this whole thing is equal to 0, and if you look closely, this dq dt is current. That's current. That's the current here, and there's current as well. So that just drops out because we have it equal to 0. And then what I can do is rearrange this a little bit. This is di dt, which is really the second derivative of charge, because I is dq dt. Bring everything else to the other side, and what I'm left with is -1 over LC times Q. And right here, we have the definition, basically, of simple harmonic motion. I have the second derivative equals some negative constant times the thing you took the derivative of. When you have this, this means that this piece right here is going to tell you everything you need. Because the square root of this, as we saw when we did simple harmonic motion, is omega. So the square root of 1 over LC is omega, which is also equal to 2 pi times the frequency, which is equal to 2 pi over the period. So that's what you're going to have. Now, one of the exercises I left for you again was to show that this is going to be related to time, that actually the square root of LC must be measured in seconds. So again, for some reason, the universe really likes this idea of inductance coil, which is nothing more than you turning some wire around a coil, and capacitance, which is really us taking some sheets of metal and putting them near each other. Those two quantities are related to time. So what does this mean will happen? This means that it's going to oscillate with the frequency that you can calculate there, and that means the charge on this, the charge on the capacitor, is going to oscillate in a nice regular pattern. Nice sine or cosine wave, whatever you'd like. But the last circuit we're going to actually talk about here, which we're going to do it really conceptually and quickly, is this. What if instead, because this is a little bit more realistic, we had an LC circuit, so there's the inductance coil and the capacitor, but then we had a resistor in here. Some people call this an RLC circuit, some people CLR, it doesn't really matter. But this is more realistic because there's no such thing as having those wires without resistance anyway, unless you have some kind of superconductor, so that seems a little silly for this. But in this case, what's going to happen is it's still going to oscillate at the same frequency that we saw before, but now you have damped harmonic oscillation. So in an RLC circuit, what we see is that the charge on the capacitor will do something like this, where it'll just get smaller every time, and it'll die down in damped harmonic oscillation. So what we saw today was the LR circuit, and the LR circuit is really sort of a backwards version of an RC circuit, where you have, when you first turn it on, it resists the change, so it doesn't let anything through, and then after a while, it just lets it all through, and then you have basically a wire from the inductance coil. Turn it off, the inductance coil powers the circuit, and then after a while it dies down because you have energy loss through the resistor. And then we saw an LC circuit, which is basically just an oscillating circuit, but a more realistic version of that was the RLC circuit. So you can go ahead and dive into worksheet number 3 now. Feel free to email me if you have any questions, and hope everybody's doing great, and hope to hear from you.